Okay, so here is how we start to calculate the joint density. Again, nothing special, all the same situation. If we know the cumulative distribution, we just differentiate the cumulative distribution and we can get the density. So the cumulative distribution for the random variable z is just the probability that z is less than or equal to a. And that's the same as the probability that x over y is less than a, or x less than or equal to a times y, since both x and y are positive numbers, right? So inequalities don't change here. And then I just have to realize what sort of baking pan is this, where x is less than ay, which means one easy way to describe it in this form is that y ranges anywhere from 0 to infinity, and for each fixed y, x ranges over the interval from 0 to ay, which you see over here, right? So it becomes this type of triangular baking pan, right? So this is triangular baking pan where we describe it in terms of horizontal slices. So I select a y and I slice horizontally. I hope you can see it, yes? So integrating this expression, I see that, well, first I integrate with respect to x, and I get this expression here, and then I integrate with respect to y, and that's what I get, correct? This is just after you get it to single variable calculus, now it's pretty simple. So that's just basic integration properties. So we get 1 minus 1 over a plus 1 as my cumulative distribution, where a goes to, a starts from 0 and goes all the way to infinity. So then I differentiate with respect to a, and when I differentiate with respect to a, I get 1 over a plus 1 squared. So that's my density function. Good? So I hope many of you just obtain the same solution. It's pretty simple. So, right, we can of course create cumulative distribution functions for several random variables. So we can have many of them, and we can create in a natural way the cumulative distribution will be, let's say in this case, x1 less than a1, x2 less than a2, and so on. And then the probability is going to be the multiple integral, the multiply iterated integral, where x1, x2, all the way to xn are in the region C, right? So it's just basically by default that's so. You construct, so to speak, multi-dimensional histograms or multi-dimensional boxes, and the boxes stand for probability. I mean, it's not so crazy. It's pretty natural almost, right? You might think. And the immediate example that you can think about is multinomial distribution. So that is, for example, when you perform an experiment, and each trial of the experiment, to be precise, has a multiple number of outcomes, right? So the outcomes are, let's say, A1 through AR. And each of them has a particular probability of happening, right? So we can create the multinomial distribution, which it's a generalization of binomials. So how many times did outcome of type 1 occur? How many times did outcome of type 2 occur? All the way, how many times did outcome of type R occur? So if this sounds very abstract, it shouldn't. Imagine that what we do is just we take a fair dice, for example, we take a fair die, and we toss it 9 times. Each toss is independent, okay? So the number of outcomes here are 6 for each trial, right? So in each particular outcome has probability 1 over 6. So then let's say, what's the probability that I have exactly 0 outcomes of type 1? So I never get the number 1 in all the tosses. I never get the number 2 in the tosses. I get 4 times the number 3 on the die. I get 1 time the number 4, 2 times the number 5, and 2 times the number 6. Okay. So the numbers here, of course, they add up. They're supposed to add up to 9. Yes. So so you can just it's like assigning each toss of the die to the destiny. So 0 are assigned to outcome of type 1, 0 to outcome of type 2, and onwards, right? So that amounts to simply 9 factorial over 4 factorial, 1 factorial, 2 factorial, 2 factorial times 1 over 6 to the 9th power. It's missing, so the last result is missing something. 1/6 to the power 9, I think, no? 1/6 to the power 9 seems correct, because each particular outcome has probability 1/6 to the 9, 1/6. Did I type something incorrectly? I hope I haven't made a mistake, right? So there is a 9 here. To the power, times 4. You mean somewhere here I missed, say, you're right? What is it? 1, 2, 3, and I have more of them. You're correct. There is a typo, right? So I did not put some 1/6 somewhere, right? Thank you for noticing. Right, too bad. I hate when that happens. Pisses me off. Right, I write it several times and usually, too bad. Right, so there is something missing in here. Well, so let's go to the last lecture note, at least the officially last lecture note, which I posted today. So independent random variables, mostly something pretty simple. So we would say that two random variables, x and y, are independent if the probability that x belongs to some set A and y belongs to subset B is the same as the product of the probabilities that x is in A and y is in B. Okay, and it can be shown. That actually is easy to show if you do measure theory, I suppose, right? So it's not true for all subsets, it's only true for measurable sets. So that's something in real analysis. So it can be shown that if x and y are independent, then that happens if and only if the cumulative distribution function satisfies multiplicative property. So that is the probability that x is less than a or equal to it and y less than b or equal to it is the product of the probabilities that x is less than a and y less than or equal to b. If this is true, obviously if this is true, then that will be true. But if this is true, that's sufficient to show that you will have this property for every measurable set, to be precise. Okay, you can define it in terms of open intervals. So when x and y are discrete, you have this mass function, and then the mass function satisfies that the probability of x and y of those two events happening is the probability that this x happens times the probability that this y happens. So it has this property that we learned in chapter 3. And what you would see is that, well, it's really, again, the same thing for integration as for the sums. It's just what happens is that if the mass function satisfies this multiplicative property, the probability that x belongs to A and y belongs to B is just the summation over all possibilities, over all combinations of x and y, pxy, correct? So x being in A and y being in B. Well, I mean, don't worry about the final. You'll see it, and then you ask me the questions afterwards, right? Which hopefully, again, it takes me a bit of time to respond to, but most answers, if you miss them, are in the lecture notes. Give me one moment, guys. I'm sorry. 1 second. Something is in the door. 1 second. Yep. So, yeah, where were we? There is some strange bug, I think, with this thing, is that once I click on the camera, it does not let me pick out the cursor again. Okay, here we go. So, yeah, so this part is simply a matter of multiplication, right? So similar ideas that we used for covariance to prove that it's equal to 0. Remember when the variables were independent, is that when the mass function satisfies this multiplicative property, I can simply factor things out and I can write it as two products. So in the case of continuous random variables, the independence part of the property is also inherited by the density function. So the density function will satisfy this multiplicative result. So a very simple example of independent random variables is, for instance, suppose we have independent trials that we perform n plus m times, and the probability of success for each of the trials is p. X denotes the number of successes in the first n trials, and Y denotes the number of successes in the last m trials. It's pretty obvious that those results should be independent, and a calculation reveals that it is indeed so, because the probability that X equals to K and Y equals to J is simply out of the first n I have K successes, and out of the last m I have J successes. And you can see already that those are the probabilities that X is equal to K and Y equals to J. This probably is just the product of them. It's easy to generalize. It's very easy to generalize it's very easy to generalize independence to many random variables. So that would be when the probability that x1 is in A1, x2 is in A2, xn in AN, that ends up being the product of each of those probabilities, of them separately. So here is maybe a simple example. So in my calculus students, I have attendance that's not very, they're pretty tardy usually when they join. And let's say that each student joins the session independently, and the distribution when they join during the session is beta distribution with parameters 3 and 1. Right? So that means A equals to 3, B equal to 1. And usually there are only 12 students that come, the rest of them don't bother. So the question is, what is then the probability that 10 or more will join within the first half of the session? Can you calculate it? And the second question may be a bit more interesting, maybe not. I'm not sure how quickly you figure it out. The second part is, what's the probability that the 12 students will log on in alphabetic order? So first person, that is the first in the alphabet among them, and onwards, right? So they log in alphabetic order. You remember beta distributions, guys, right? So all it is essentially it's x to the power of a minus 1, 1 minus x to the power of b minus 1. And it has to be a distribution that's, when you integrate it, or between 0 and 1, you get 1, right? So you just have to multiply it by a normalizing factor. Let me know, guys, if you're stuck or you're just working with it. You don't need to give me the number. Well, for B, I would like to have some sort of representation for it, but A, it's enough to put it in some sort of form. Right, guys, you see, how do you remember the beta distribution? You don't need to look it up much. Beta distribution is simply, it's x to the power of A minus 1, 1 minus x, B minus 1, and correcting factor. So this has to integrate to 1 between 0 and 1. Okay? So in our case, B is equal to 1, so 1 minus x doesn't exist, so you just x to the power of 2. So the distribution in our case is nothing more than just x to the power of 2 multiplied by the appropriate constant. Okay? What's that constant? Figure that out, and then you can figure out the answer to A, I hope. Most of your faces, guys, I don't see. Are you puzzled by this question, or is it easy?
Go with a goodwill vector that's proportional to spend. That
So let me know if you're puzzled by this problem or you're finished, so to speak, or at least finished with some part of it. Well, shall we proceed with the solution to part A, and then we'll see what happens with the other part here. So first, I will label the variables x1, x2, all the way to x12, because I have 12 students, and let's say the labeling is in accordance with alphabetic order. So this person is the first in my alphabetic list, this is the second person in my alphabetic list, all the way to the 12th. And then for each of them, that's the time when they log on in the session. So 0 means at the very, very beginning of the session, and 1 means pretty much right when it's over. So then, because the distribution is beta for each of them, that means that the function that we're interested in is, since by the beta it has to be x squared, the correcting constant is 3, correct? Correcting constant is 3, because the integral from 0 to 1 of 3x squared has to equal 1, and it does. Good? So the function is, the density function is 3x squared for each individual. So the probability that the person K joins within 1/2 or earlier of the lecture is the integral from 0 to 1/2 of 3x squared, which is the same as 1/8. Correct? And now, if that's the case, what's the probability that at least 10 people will join before half of the class is over? Binomial, precisely. It's now binomial because now each independently is a success or failure, right? So person 1, success or failure. Person 2, success or failure. So now the question is simply binomial with success probability of 1/8 for each trial. So we have 12 trials. And that means that the summation is simply from k equal to 10 or 12, up to 12. Of 12, choose k, 1/8 to the k, 7/8 to the 12 minus k. It's that binomial, right? Which, if you estimate it, it will be roughly 4.8 divided by, what is it, 10 million, right? So it's very unlikely that all of them will join before half of the lesson. Now, second question is what's the probability that the students, once they join, when they are joining through the session, they join in dictionary order from first person on my list all the way to the last person on the list. What's the probability of that? That might be useful for your final. In other words, x1 has to join first, so his time is first. Second person is time is next. So in that order. Okay. Yes, yes, Ugo, exactly. Wonderful, Ugo. You got it. It's exactly right. Right. So by symmetry, so integration would have been rather complicated, right? So we can set up an integral containing 12 integration signs, right? But that will be a very complicated way to do it. By symmetry, you can see that it's each of them is essentially the same individual and acts independently. So this is one arrangement, and there are 12 factorial possible arrangements. Each of those possible arrangements has the same probability by symmetry. So without any calculations, it's pretty clear that it's 1 over 12 factorial. I hope it's clear to everybody, guys. Yes? So it's 1 over 12 factorial. Cool. Here is also a similar problem. So try to solve it. Men and women decide to meet at a certain location, and they have to meet between 12 and 1 p.m. The question is, what's the probability that the first person to arrive waits for the second 10 minutes or longer? Make sense? So two individuals arrive between 12 and 1 o'clock. And the question is, what's the probability that the first to arrive waits for the second 10 minutes or more? Some question of the sort many, many years ago was on some CUNY first challenge, I remember. Well, you have to be careful. Sure, it's a double integral of 1 over 60 squared, but what are the bounds of the double integral? That's what we have to be. That's what we have to figure out. When you're ready, guys, you just let me know. Yes. So I don't make you wait. Wonderful, Hugo. So except you have to be careful, not from 0 to 60, because then x minus 10 will be below 0. So you just have to adjust a little, right, for the first integral, not from 0 to 60, but from 10 to 60. So here is how we can reason it out, guys. So x and y are the times that, let's say x is the time when woman arrives, y is the time the man arrives. So we are interested in the probability that either x plus 10 is less than y. In other words, the moment at which the woman arrived plus 10 more units is smaller than the moment at which the man arrived, or vice versa, right? So man arrived first, then waited another 10 minutes, and the woman arrived even later than that, right? So that's what those mean. And they are disjoint, of course, right? So if this happens, the second part cannot happen, so you can write it as a sum of those two probabilities. By symmetry, since there is no difference between x and y, by symmetry, it's enough to evaluate 2 times the probability that y plus 10 is less than x. Yes, because this probability and that probability are clearly the same. So what is this probability? So x has to be bigger than y plus 10, which means y has to be smaller than x plus 10, x minus 10, I'm sorry, right? So first, for that to happen, right, if y arrived at, so to speak, at, well, if y arrived at 0, then x arrived at least at 10 minutes. So when you set it up over this, it means that x starts at 10 and goes all the way to 60, right? So x has to come at least 10 minutes late to the appointment at 12. And the x would have to, of course, the last time x can exist is at 60 minutes. So the integral is from 10 to 60, 0 to x minus 10. That's when y arrives, right? And then with 1 over 60 squared dy dx. So you can factor out the 1 over 60 squared. And now it becomes a simple matter of integration. And the answer is 25 over 36. Yes? So here is one more example. And this might take you some time to figure out. I think it's a bit interesting, right? So it's one of those similar to some of the other things that we considered. So imagine that we have a table or a very big infinitely ruled flat surface. So let's call it a table. And it's ruled with equidistant parallel lines, right? So there are parallel lines, and the distance vertically between one line to another is always equal to d. And then what you do is you throw a needle on this table, and the needle is of a length shorter than the distance between the lines on between the rulers, so to speak, right? And we throw randomly. We throw the needle randomly, and the question is, what's the probability the needle will intersect one of the lines? The question makes sense? So it's kind of like this. So we have table, there are lines, right? Like this, infinite or something, right? So you toss and you toss a needle. So the needle, let's say maybe it's like this, right? The needle fell, so that's an intersection. What's the probability the needle will intersect one of those lines? That's the question. I'll be right back, guys. Interesting, yes. So in 4 minutes, I will tell you how I thought of it. Okay. So if you can set it up, that's great. One more minute, guys, and I will reveal the answer. All right, guys. So I hope you thought about it. I hope the problem was interesting. I'm sorry. Maybe I should have waited with revealing it a bit longer, but I'm not quite sure. I'm not sure what you're doing there, right? So there are still lots of interesting problems to solve. So here is how I thought of it, right? So clearly the needle falls somewhere, right? It's in between two bars, right? Somewhere. So I can always imagine that wherever it falls, it's always, I can just re-identify it to within two particular bars, right? And what I can always do is wherever horizontally, wherever the needle falls, its leftmost point will be I will draw a line through the leftmost point, correct? I draw a line through the leftmost point, and that line here, dotted line, is of length d. So far, what I'm saying is clear, guys, right? So imagine it's an infinite paper, or or basically the for this problem to be true is that the needle is equally likely to fall anywhere within each of the ruled bars, right? So it falls somewhere, and where it falls, I can just readjust and say this is one level, this is another level, and here I have a dotted line, which I draw always through the leftmost point of the pin. And I can further simplify the problem. You see, so it could happen that the needle is intersecting the bottom line, or it intersects the top line. So I can always assume that when intersection happens, that happens with respect to the top line. And how can I do that? I can always flip. I can imagine flipping this piece of paper over or looking underneath it if it's here. Or if you don't like those transformations, I can imagine that, well, the angle that the needle makes with respect to this vertical line is either drawn here, if it intersects the bottom part, or it's drawn here. And I can just I can see that all the angles then from angle 0 to angle pi over 2 are equally likely, right? So the needle, it could only be horizontal or point up or point down, which I can always assume it's pointing up, because I can always assume that either the angle is here, it's a particular angle theta. Let's say this is 45 degrees. So then I can assume those are the 45 degrees up. So by symmetry, I can imagine that what happens to the needle is that you randomly pick a y value between 0 and d, and you randomly pick an angle between 0 and pi over 2. So before I proceed, guys, acknowledge that you still are around and maybe say, oh yeah, I get this idea, or re-explain something, please. Hello, Josh. So you understand what I'm talking, I think, right? Good, Shalomit, right? You all get how I basically reason it out, and it seems that wherever the needle falls, there is going to be a leftmost point of the needle. And again, intuitively, it seems that the leftmost point on the needle is equally likely to be anywhere between any two bars. Could be either on one of them or on another, and anywhere in between. Right, so that's one random point selected for the needle, and of course, needle is it has some angle with respect to the bar. The angle is either opened from below or opened from above, and I can always just readjust the angle to say basically it's always opening from above. Or another way to say that, instead of flipping this piece of paper, is to say that I just measure the absolute size of the angle. Just if it's 0, it's either like this or like this. If it's pi over 2, it's either like this or like this, right? I can just always kind of fold it together, so to speak, with respect to the angle. Good? So in essence, then what do I have? I have two randomly distributed variables. It seems that they're independent. Y is independent of x. Where it lands is independent of the angle. That I'm assuming by intuition, right? I mean, I don't see any reason why given this point, this angle should be small or large or anything, right? I cannot predict it based on knowing that part of the needle was here. Good. So now I have y randomly distributed between 0 and d, and theta randomly distributed between 0 and pi over 2. Good. And you can create a joint distribution, right? So theta has a density function which is 2 divided by pi, correct? Because between 0 and pi over 2, I have to correct, right? It's a rectangle between 0 and pi over 2. The altitude must be such that the area is equal to 1, right? So the altitude must be 2 over pi. And for y, the altitude must be 1 over d. Good? So the density function is 2 pi times 1 over d, or 2 pi d. So far, what I'm saying is, I hope, is completely understandable, right? So where theta can vary from 0 to pi over 2 and y from 0 to d. And now the calculation is now, what's the probability of intersection? Again, in this case, I'm assuming only intersection possible with the top line. It's the same, right, by symmetry, right? So only top line intersection I'm considering. So what must be true is that y plus L cosine of theta, so y plus L cosine of theta is bigger than d, or equal to it, right? As in here, right? So project cosine, I'm getting y plus this segment is more than d. So I am asking for the probability that y plus L cosine theta is bigger than or equal to d. Good? And that's the probability that y is bigger than or equal to d minus L cosine theta. And this I can set up. So theta can be anything between 0 and pi over 2. And for a particular theta, then y has to be between d minus L cosine theta. That's the smallest number it can be, and the largest value it can be is d. So I integrate it. It's d minus this expression. So it ends up being simply, here I just wrote. So it ends up being 2 over pi d integral L cosine theta d theta, which is 2L pi d, right? 2L divided by pi d. And the last very simple question is, suppose we have 3 independent random variables, x, y, and z. What's the probability that x is bigger than or equal to the product of y and z? So the first random variable is bigger than the product of the 2 other random variables. What's the probability for that? Just set up the integral. I mean, I'm assuming the question is simple for you guys, yes? Well, so are you ready, I guess, right? It's simple? Yes? No. A lot of you play poker, so I think you're good with those things, right? Well, so again, how do you solve this? Very simply, if they are independent and each of them is between 0 and 1, then the density function is the product of the density functions, okay? And the product of them obviously equals to 1, because the density for x is 1, the density for y is 1, the density for z is 1. So the product is 1. So we're integrating over x, y, z in 0, 1. We're integrating what must be the case. Z is between 0 and 1. Y can be anything between 0 and 1. But x has to be bigger than yz and less than 1. So we just integrate this expression. So what it becomes, and here maybe that's only a very simple practice for integration. So I integrate the inner integral, that's simply 1 minus yz dy dz. Now it's easy to integrate 1. Integral, double integral of 1 is just the area of a cube. And so the volume of a cube, so that's 1. And now it remains to integrate yz. The integral of yz can be solved very simply. You can factor them out. It's the integral of 0, 1 y dy times the integral from 0 to 1 of z dz, or simply the integral of y dy squared. Yeah? It's just like summation, it's just you factor it out. And this equals to 1/2 squared. So it's 1 minus 1/2 squared, or 3/4. And well, that is, I suppose, what I have for today. I'm not sure what sort of how you found this class, by the way. Did you find it easy, too easy, or rather hard? You gave me the impression, at least many of you, that it was pretty easy for you. You need more challenging material. Am I correct? Yes?
It was moderate.
Moderate. Okay, that means moderate means I need to aim to make it harder. Yes?
No.
Not
No?
really.
No?
No, no. But I really enjoyed it, especially that it gave me the background of like mathematically understand the statistics equations, especially the random variables. So I really enjoyed it, and it was really useful for me.
I'm very glad. It's an interesting class. I mean, I always learn every time. I taught it very few times. I learn new things, right? There are still so many interesting ideas to consider.
Yeah.
All right. So good. So I'm glad if it were challenging and you learned something from it. Yeah. So I really enjoyed. Truly, I mean, I enjoyed trying because I haven't seen most of you. Right? I forgot what you look like. Most of you are black boxes here, but it was nice seeing you when we were in class. It was nice imagining that you exist when I'm here. Okay, and of course, you know, if you ever feel like you know, something kind of comes up, you want to talk about something, I'll be happy to see you. Right? So yeah, it's too bad. I'll miss you. Definitely, I'll miss you.
Yeah.
Yeah.
Thank you.
Yeah, guys.
Thank you.
Take care. I will work on the final. Once it's ready, I will let you know. And by the way, another thing, so I know for the future, how bothersome were the things I sent you? Very bothersome, to not bothersome at all, to pleasant, maybe. No, you will not tell me, probably.
I think it was
but you can talk to me. You know, don't worry. I don't get angry. Some people do, but not me. I cannot get angry. That's my problem.
Yeah.
All right. I am trying to, you understand, I mean, truly my nature, if you haven't understood, it's very, very simple. It's very virus-like, truly, right? So I want you to be copies of myself in some sense, like many Arkadys. So, yeah. All right, okay. So I really enjoyed this class very much. It's too bad, you know, they stopped it short somewhere. Only one person. You see how much I don't know people, right? Okay, only one person said like, "Oh, what are your plans to a while, like maybe 3 weeks? What are your contingency plans?" I'm looking contingency plans. I thought maybe they will cancel school, but surely they will not cancel Super Bowl. Surely they will not cancel going to the malls or going to restaurants. So why? I mean, it would be making no sense. But I guess my understanding of human nature is flawed, very flawed.
One thing that for sure I understood was that online class is way less efficient than in person.
Not efficient at all. I mean, I spend all the time writing those lectures for maybe a quarter of it. Although for me, I never like classes. I don't know how you can learn from a class.
I hope next semester they...
Well, they might be still, who knows how frightened, right?
Yeah.
But they're still more or less okay. You know, at least on the street, I mean, it was pretty interesting. It's like mushrooms. I see no person. In the other class, there was one girl that was an early adopter. She came. Nobody is wearing a mask. He comes there wearing this mask, and she's the first. That's pretty brave to do that, right? And then everyone, like every single person, I forgot what people's mouths look like. Right? There is, if you want, I'll send you this, some YouTube suggested some Russian rap song regarding that. I'll send it to you. All right. All right. So the final timed. I mean, timed is try to finish it so that I can grade it before the grade is posted. I mean, the grading is I'm hoping that, guys, that I give you a lot of time so you don't feel the need to copy it, right? So you don't feel pressure, that you feel like, well, it's enjoyable and you will learn it. Third exam was canceled, but interestingly enough, the other class, they did not want to cancel third exam. They figure the final is departmental, and I guess it's harder to cheat there. I hope, guys, that you read the book that I suggested. It's a pretty good book, right? And yeah, pretty interesting book about the Gambler. At least in Russian, it's good. All right, so so you see, some person, so Hugo says it's better online. Well, guys, right? So I will send you that rap song. I don't know if you want anything else from me, right? You should watch. I mean, I really enjoyed this guy that I translated. You see, I mean, I first did not want to bother it, but once I'm pretty, well, the reason I translated those videos is I go through the cemetery, right? And now it's crowded. Like, people are lying there, like, on the beach, but they are all wearing masks, right? And like, I'm just looking at it. They first of all crowded my cemetery. They made it into like a resort, right? There is like a pond there, and they're lying and baking in the sun with children and everything. Tons of cars. And all of them are wearing masks, right? All of them, right? Except, and then there is one little girl, and she looks at me. She was not wearing a mask. She looks at me terrified, and then she puts a mask on, right? So that pissed me off so much. I just figured, I'm now translating this. I should not go out, otherwise I do useless things. Yeah, who knows what class I'll teach, guys? It's not known. I asked for to teach this, right? Because again, another thing that bothers me is, statistical things. Pretty interesting what, decision-wise. One person regarding statistics, there will be a question on the final regarding that, actually stopped talking to me because of statistics, because of probability, right? They got so upset, I'm not quite sure exactly by what, but so very, very upset that blocked me on the phone. The question will be on the final in a form that hopefully doesn't bother you, right? Let's see if you recognize it.
So we will receive the final over the weekend, and then we'll have how many days?
How many days? Well, I will let you know precisely how many days. It's just you see, ideally at least 3 days maybe before I have to post the grade, right? I'm a bit loose about it. I don't know what's precise date for me, right? I haven't even checked exactly when the deadline to post it, but that's pretty much my my deadline, is that I have to post by a certain time. If I don't do that, I cannot post. I don't have access to the system. So my deadline is essentially my ability to make it to the deadline. But hopefully, since I'm not writing the lectures, I will be able to grade you very fast. I'm hoping, right? Unfortunately, so to speak, spring is here, and my torture is back. I'm not the only one who is. There is somebody who is pecking at me. All right, for the research. Right? So, like, he's like, we are going to work very, very hard. Right? I was hoping you forgot about me. Right? I started getting scared that they will lift the curfews. Anyhow, guys, so it's so nice to see you. I hope I will hear from you. I want to teach in the summer. I thought maybe to teach analysis. That's the videos are posted. I'm not sure. You can try at least the first lecture. You can see how my borderline when I was still a little bit young, right? And then I stopped being young and stopped being so fun. So, but that was kind of the first time I started recording. So, if you do join to that, or if you want to, possibly there's another student from years ago actually asked me to do an independent study over the summer. I had no choice. So maybe if you're interested, we can talk about reading an analysis book, measure theory. Yeah? Graduate level, you can kind of understand it. I'm sure I know some good books. So if you read it, we can talk about it, since I suppose for him I'll be reading it. So if you're interested, you can join our discussions. Sounds good?
Yeah.
All right. Yeah. I mean, I know it's yes. It means no, but goodbye then. Goodbye. Take care, guys.
Bye.
See you. Mr. Post of all, my brother says. So he's a very cynical bastard, my brother. Right? He's right at the corner. TYSM. Thank you so much. Yeah, you see, I am improving.
Getting better. All right, bye.
All right, bye guys. Take care. Danke, ja. Elina, hast du diese Videos gesehen? Oh, Brittany, have a great summer too. Oh, you learn German, Rusima, don't you? Gute Nacht. You're learning German, Rusima. How can you haven't told me, right? So now you have to write messages only in German. Once people tell me they do that, it's now your requirement. So only in German. Wie viele Jahre hast du Deutsch studiert? Gut, aber in der Hochschule kann man wirklich nichts lernen. Ich habe vielleicht 6 oder mehr Jahre Französisch studiert oder gelernt, aber wirklich davon weiß ich nicht. Davon kann ich fast nichts, davon kann ich an nichts erinnern. Oh, Charlene, so nice to not, unfortunately, I remember you said you will come to the cemetery, but no, you have not. Too bad. Well, guys, I'm going to disconnect it. I'm assuming you left, so goodbye. Take care.